And hello AP Physics students, this is Mr. Kirsten coming at you with another example problem. Today we're going to be looking at Chapter 11, problem number 30. All right? And this problem has to do with pendulums, and we haven't worked with pendulums a lot, but here's what you should know. For small angles, pendulums exhibit simple harmonic motion. And remember that simple harmonic motion, we abbreviate SHM here. All right? So remember that in our previous problems we had stated that the period of a, previous problems we had started the period of a mass in a spring is 2 pi square root of m over k. We're going to learn today that the period of a pendulum is 2 pi square root of L over G, where L is the length of your pendulum. So the length from, say, the top of the string down to the center of mass of your object, right? So this is a pendulum. It's going back and forth. So that's L. And G is your acceleration due to gravity on the Earth. Notice that the period of the pendulum is independent of the angle of the swing. This is why pendulums can be used in grandfather clocks, and no matter where the clock is or what kind of angle it's swinging through, the period of the clock will be the same. Usually, I think on a grandfather clock, one period is actually 2 seconds. All right. So in this problem, it talks about a pendulum that is on the Earth. Right. So let's say this is the Earth. And it states that the period of this pendulum on the Earth is 0.80 seconds, and it wants to know what would the same pendulum, what would the period of it be on Mars, right? So we could just send this pendulum up on the Mars Curiosity rover and see how it goes. Okay, here's the plan here. Why don't we take this equation for Earth, square root of L over G, and we should know everything in this problem. We know the period, we know 2, we know pi, we know G. Let's solve this for L, okay? So if we square both sides of the equation, we should get this. And if we rearrange and do a little algebra there, we would get that we'd take the period squared times G divided by 4 pi squared. Right, so plugging in here, we get 0.80 squared times 9.8 divided by 4 times 3.14 squared. And we would get that the length of our pendulum is 0.16 meters. Okay, so we know the length of our pendulum. We know that G on the Earth is 9.8. All right, let's take our pendulum and let's go to Mars. All right. So G on Mars, acceleration due to gravity, should be much less, right? So the period should be greater. Smaller G, larger period. I think there's a conceptual question about if you take a pendulum, a grandfather clock, and move it to the top of the mountain, what happens to the clock, right? Okay, so let's talk about Mars here, the planet, not Bruno. All right, so, I'm running out of room here. So the period on Mars would be 2 pi times the square root of L over G, where G is the acceleration due to gravity on Mars. And we solved for this in an earlier problem, taking into account the mass of Mars and the equatorial radius of Mars and that type of thing. Okay, so if we plug this all in here, we would get that the period of the same pendulum on Mars would be 2 pi times the square root of the length, 0.16, so the length of the pendulum hasn't changed any, divided by the acceleration due to gravity there. Okay, so remember when you're using this formula, make sure you've got your length in meters, since G is going to be in meters per second squared. So if we plug in those numbers, plug that all into our calculator, we get that the same pendulum on Mars would have a period of 1.3 seconds This is on Mars, on the red planet. Okay. So let's review here. So we have our formula for the period of a pendulum. Just depends on the length of the pendulum and the acceleration due to gravity in that area. So a pendulum that has a period of 0.8 seconds on the Earth would have a period of 1.3 seconds on Mars. All right, well, thank you very much, physics students. We stay tuned for your funny joke. All right, and since today's joke was about Mars, we have a joke here from the website xkcd.com, number 695. Oh, look, it's the Mars rover on the red planet, day 1 of 90. Oh, the Mars rover's in 89 days to go. Oh, and then look, day 88, only 2 days until I get to go home. Oh, day 91, the rover's like, hey, my gosh, what's going on? Day 103, maybe I didn't do a good enough job. Maybe if I do a good enough job, they'll let me come home. Day 857, I thought I analyzed that rock really well. It's okay, I'll do the next one better. Day 1823, sandstorm, power dying, but a good rover would keep going. A good rover like they wanted. Oh no, I'm stuck. Didn't I get to go home? Didn't I, guys? It's funny because rovers don't really have feelings, but they're kind of making it like it did. All right, you should check out the website XKCD. It's got some really funny stuff. Nice work, AP Physics students. Have a good night.